Let's look at the differential equation dx dt plus x squared is equal to x. Now this is not in our form, so I'm going to get it into our form where dx dt is equal to some function of f of x and y. Now we can make a little kind of visual note here that this is a function of just x, so this is an autonomous equation, which means we can do a little bit of work with our graph here. If I look at x versus dx dt, well, x minus x squared is dx dt, which is x times 1 minus x, which has a critical point at 0 and a critical point at 1. And so if we graph this, notice it's a negative parabola. So it's going to graph up here, right? Get my vertex correct here. And shoot down and shoot down. Negative parabola. Well, if we look at what's happening, this is a negative change. So that's going to cause x to want to move to the left. This is a positive change. That's going to cause x to want to move to the right. And this is a negative change. That's going to want to cause x to move to the left. Which means this is an unstable critical point. See, we have an unstable critical point and a stable critical point. Which means if we continue and look at a graph of x versus t, and we plot our critical points on it, and I'll do that in orange here. So this is x equals 1, this is x equals 0. Then your function is going to tend to come down towards x equals 1 asymptotically. It's going to be pushed away from x equals 0 and up to x equals 1 asymptotically and pushed away from x equals 0. And so we're going to have solutions like this. This means if I start at x equals 1, I'm always going to be x equals 1. And if I start at x equals 0, I'm always x equals 0, but any perturbation is really going to have it fall into these regimes. So we really won't see this as being any type of stable solution on it. So let's see what separation does for our equation here. So I'm going to divide both sides by x minus x squared and multiply both sides by dt. I'll take my integral on both sides. And if I go into Chalmers and look up my integral here, I'm going to recognize that an integral in the form of dx over x times ax plus b is equal to the natural log of x over ax plus b plus a constant. So if I use that integral form, my left-hand side is going to be the natural log of x over 1 minus x is equal to t plus c. I will raise everything e to the power of this, so that clears this, and I'm going to get e of t plus c. or x times 1 minus x equals some arbitrary constant, e to the t. If I cross multiply, x is going to equal k e to the t minus k e to the t times x. I'll bring all the x's to one side. I'll factor out an x. And that means x is equal to k e to the t over k e to the t plus 1. And so this is our solution in here. We're also going to, and different values of k will set different, based off of different initial conditions. We also have that we'll look at this solution when x is 1, defined as 1, because it's a stable solution that we can look at.